So first of all, you can understand me better because we asked to put down completely the volume of the room. Only people online can listen through the microphone, but maybe this is better. Second, I really would like to thank the organizers for inviting me here. I see in the room Santi Chillemi and Angelo Di Garbo, and I remember always that one of my first invitations was in Ischia, a very famous conference you both organized long ago. So today I would like to present some recent results that we obtained, and when I say we, I'm meaning this rather large collaboration involving people from Spain, Italy, Israel, China, and Russia. We recently obtained on the structure and dynamics of networking systems in which interactions, which are higher order interactions, are extremely important, okay? And I like to start this presentation saying that in physics, you can roughly divide two kinds of systems. You have the continuous systems, which are those which are described by partial differential equations. And usually the way you study complex behavior in this kind of systems is through the emergence of patterns, so the formation of patterns and the competition of patterns out from the equilibrium of that system. And these are the continuous systems. And then, as opposed to this continuous system, you have the distributed systems. That is, those systems which are formed by a myriad, a very large number of unitary components. And these unitary components are interacting among them. And the way these components are interacting actually determine the collective behavior and the collective functioning of the system itself. That's why in the last 20 years, I would say, as a rather normal continuation of classical graph theory, there was the emergence of a movement in science called the complex network theory, which was rather successful because it was indeed intended to model as networks these kind of systems like internet, like the brain, like many other distributed systems where the components are modeled as nodes and the interactions are modeled as links, okay? Links between these nodes. Now you understand that there is a very strong assumption you are making when you represent these systems as networks. And the assumption you're making is that each component, each node is interacting with the rest of the system by means of a term which you can always factorize as a sum of pairwise interactions, because a link is a pairwise interaction. So you are saying that this fellow has an interaction with the rest of the system you can always write under the form of a sum of a given number of pairwise interactions. And you realize that this is always true, for example, when the interaction is linear. So if you have, for example, diffusive-like interactions or something like this, you can always find a way to factorize. But when instead the interaction is nonlinear, then in general, this assumption is very short. And you have a very huge number of examples in which instead you have to consider interactions which are many body interactions. That are 3 body interactions, 4 body interactions, and they cannot be simply factorizable into the sum of pairwise interactions. Make you some few examples if this works. Next slide, please. Next slide, please. Doesn't work. Okay. So the first example, imagine to map the co-authorship in scientific papers into a network. Nodes are scientists and links are papers. Interactions are papers. Now you have here the case of 3 scientists, I, J, and K. And I and J publish a paper without K. Then J and K published another paper without I. And then there is a third paper published by I and K without J. So there is a triangle. There's a triangle in this network, which is, however, the sum of three papers. So it's factorizable indeed in the sum of the three, because there are three elements, three links. At variance here, you have the case of a single paper co-authored by the three people. Here you have a group interaction between these three, and you have to distinguish this because you have only one paper made by the three of them, and not three papers made by pairs of them. So this is a clear case in which you cannot factorize. Another case, for example, in ecology, but also in chemistry, imagine that you have species, which are the nodes of the network, interaction between species, but then you have a species like here, species 3, which is catalyst of the interaction between 1 and 2. In chemistry, you have 1,000 of examples like this. So species 3 is not directly interacting with 1, is not directly interacting with 2, but is interacting with the link between 1 and 2. So you cannot factorize this into different links. Means you have to take into account higher order interactions in your network. And we will see other examples later on. So when you do this, then you have immediately to pass from a matrix representation of your systems, where each link is an element, 0 or 1 of a square matrix, into a tensor representation, where each group interaction, each hyperlink, is involving more than one node. In this case, D nodes. And you have to generalize some concepts that you normally use in network, like the degree of a node I, which is number of connection that node I has with the rest of the network, into the generalized D degree of node I, which is the number of hyperlink which are formed by node I. Or the generalized D degree of the link, which is the number of hyperlink in which node I and J are simultaneously present. And by means of this, you can construct generalized Laplacian matrices in a proper way at each order of interaction. And now, you know, when you pass from this description to this description, several problems arise. There are problems regarding structure, how you redefine the fundamental network property. And there are problems regarding the function in the dynamics, which kind of new dynamics, this kind of interactions, this higher order interaction are producing. And I'm trying now to give you some few samples of recent works we have done in structure and dynamics. So let's start with structure. And probably the most important structural problem in networks is ranking the nodes. Because, you know, classical graph theory, I mean, if you take a random graph, all nodes are identical, so they have the same importance. In real-world networks, nodes are strongly heterogeneous. You have to rank the importance of the node. It's fundamental to rank the importance of the node. Think about Google. The entire business of Google is ranking nodes, because it ranks for you the web pages when you make a search. Or imagine in biology, you want to rank the importance of a protein for a mutation, of a gene for a disease, etc., etc. Now, the main idea is that when you have such higher order interactions, you may imagine to have this situation. The real representation of collection of nodes and collection of hyperlink, which may be hyperlink normal link, like this one, connecting 4 or 5, or 3 bodies interaction, which are the green ones, or 4 bodies interaction, which are the yellow one, 5 bodies interaction, and so on. So the interactions are not limited to links. And now the idea is that you can have different processes which take place at different orders of interaction in the same network. And the ranking of a node, so I mean, the question how important is a node in a network is ill posed, because the right question to ask is how central is a given node in a network with respect to a given process. So you can have a node which is very important for a process, but not so important for another. Okay? So this has been solved by us recently in a paper which is now under consideration, in which we say, okay, for doing this, we need to define a vector centrality. So not a single scalar for each node, but a vector of dimension d, where d is the highest order of interaction, -1, that you have in your system. And there is a unique way, we have proven that there is a unique way to define this vector centrality, especially each component of vector centrality, by means of the use of associated line graph and so on and so forth. I'm not going to enter into details. You can check, there is in the archive our contribution. But the main idea here is that, when you have a node, each node has one vector, so that you can make different rankings. You can make a ranking of a node with respect to the first component of the vector, a ranking with respect to the second component, to the third component, and then compare this ranking to see if really a node which is important at a given order of interaction is important at all order of interactions. And then you see something interesting, that is, if you, for example, take real-world hypernetworks, this is the archive, section mathematics. You extract 500,000 papers co-written by the 230,000 authors. So the authors are nodes, and these papers are hyperlinks, because you have papers written by 2, by 3, by 4, by 5, by 6 authors. And then you extract the ranking, the top 100 in the ranking with respect to the ith and jth component of the vector centrality. And you ask yourself, if you are a scientist which are very top with respect to 3-body interaction, are you very top with 4-body interaction, 5-body interactions? And you see that outside the diagonal, the overlap between this top list is very little. So in general, this is not the case. In general, mathematicians prefer to work with a very well-defined number of collaborators. They don't like to change the number of collaborators. So this is the case in which having a vectorial ranking makes importance, because there are different leaders at different orders of interactions. You can make the same for commercial drugs. Commercial drugs are made of different components. You have paracetamol, ibuprofen, and so on and so forth. You have each drug is some percentage of a component plus some percentage of another component. So you can map everything into a hypernetwork where components are the nodes and the drug are the hyperlinks. And here you see that if you take the top 100 list, again, you have specialistic components. So there is not such big difference between such big overlaps between the ranking. But if you limit yourself to the top 10, so really the top leader 10 components, you see that there are components indeed appear at each order of interaction at different orders. So this means that you really have to pass from a scalar description of the centrality to a vectorial description of centrality. You can make different examples. In this paper, you have the analysis of at least 20 different real-world hypergraphs, in which you see that in some cases leadership is very limited to the diagonal of these curves, and some other is spread over the curve. And of course, all this information would be impossible to retrieve only with a scalar centrality, because you have only one ranking and one one number. Then, going to dynamics, what you can do is extend to this kind of higher order interaction, typical dynamical process that you describe. One is evolutionary games. In evolutionary games, you have, in general, agents which play strategies. You can be usually binary strategies, cooperation and defection. There is a matrix which is called the payoff matrix, which defines the games and tells you how much a cooperator does when it meets another cooperator and so on and so forth. Then you collect the payoff, and typically you have to decide the next strategy by, for example, imitation. That is, you look your neighborhood, you look who is the most successful node, the one who did the best payoff at a given time, and you try to imitate with a given probability, which typically is taken to be the Fermi probability. That is the fermionic probability, the probability of having a fermionic particle at energy A, where energy is now substituted with the payoff. Now you see that if you take the classic payoff matrix and you parameterize with this S and T, you can, depending on the value of S and T, obtain the 4 principal evolutionary games. The most famous one is the prisoner dilemma, which is here. Then you have harmony games, no drift games, staggered games. And this game corresponds each one to a different Nash equilibrium. That is, the system, if you prepare with this parameter, obtain an equilibrium which is a different one, depending on the color where you are in the parameter space. For example, prisoner dilemma is very well known. Everybody has to be defector. In harmony game, everybody has to be cooperator. And in these other 2 games, you have mixed situation, which half of the population or a portion of the population cooperates and a portion of the population defects. The point here is that when you start from initial condition, in a normal evolutionary game, you get to the Nash equilibrium, then you are frozen. So each one of the member of these agents, each one of the agents is destined to be a zealot. From one time on, it will always cooperate, it will always defect, depends on which is the state in the Nash equilibrium, which is not very realistic. I mean, in normal condition, me and Angelo Di Garbo are very close friends, we cooperate. Then we clash and we defect. Then we make peace, we cooperate again, and so on and so forth. So there should be something which is inherently prohibited in Nash equilibrium. Now, how you extend this? Okay, if you now consider 3-body interaction, for example, you have to distinguish the case of the filled triangle from the case of the unfilled triangle. So in one case, you have interaction which are 2-body, and in this case, you're supposed to play a given game. And in this case, instead, you have a payoff here between I and J, which must depend on the K. And so in this case, you have to take not a payoff matrix, but a payoff tensor, which you can construct, for example, saying if the strategy of K is equal, you play game 2. If it is different, you play game 3. And then you collect the payoff, and by choosing, game 1 equal to game 3, you can put in competition different evolutionary games. So imagine that you construct a network of all triangles, and you now have a parameter here, rho, which is the fraction of triangles where you have real 3-body interactions. And you see that in all possible competitions, there is always a transition from cooperation to defection or defection to cooperation as a function of rho. That is, as a function of the number of 3-body interactions. But what is much more important is that close to this transition line, doesn't work, okay, you have the emergence of a new state, which is an asymptotic, non-stationary state. A state, you see here, where there are epochs in which cooperation prevails on defection, but then defection prevails on cooperation. Then cooperation prevails again on defection. So in these states, each agent is free of changing its position in time. So this is not, it's a new sort of equilibrium, In dynamical system, we would say Nash equilibrium is a fixed point. This is not a fixed point, it's a non-stationary asymptotic state. So this is a completely new thing that appears thanks exactly to the presence of three-body interactions. So this is, for example, something that you can do on games. Then, again, you can describe interactions in dynamical systems in this kind of hyperlinks. And we have recently extended the master stability function approach to the hypergraph situation. That is, we have considered each node of to be an m-dimensional vector whose evolution is ruled by some function fxi, which describes the local evolution of the isolated dynamical systems. Plus, you consider pairwise interaction, three-body interaction, d+1 body interaction. And you see, basically, you introduce this interaction function, G1 xij, G2 xix, J1 xj2. And so GD, they are a function of many points that describes how these dynamics are interacting at different orders. Then you have different summations here. 1 sums, 2 sums, d-1 sums, and different coefficients, sigma 1, sigma 2, sigma d. Okay? You can show, I don't enter again into details, the full details is contained in this paper, which appeared in Nature Communication last year, that as long as all the coupling functions are synchronization non-invasive, that is, when you put the equal values at the arguments of the function, you get 0. For all G, then the synchronization solution exists, is invariant. You can study the stability of this function. And you have something interesting, that is that all the terms of the interaction transforms into the generalized Laplacians. And all generalized Laplacians are symmetric matrices, that is, they are diagonalizable. The problem is that they are not commuting in general. So they are diagonalized with different bases. So you have to adopt one basis, for example, the one diagonalizing the normal Laplacian, project the error vector in that basis, and you have then a couplet system, because each other basis has to be projected in this basis. So you have one basis diagonalizing the Laplacian one, and then you have all the other bases diagonalizing the other Laplacians, which are projected into that basis by unitary transformations. And then you can show that if you have special functions, special coupling function like diffusive-like interaction and normal coupling, it means basically that the function G2 xx is G1x. That is, when you are in the synchronization manifold, in a three-body interaction, you see the other two oscillators as a single oscillator. You understand the point, more or less. And then you can map up all this Laplacian into a unique function, and you get effectively a parametric unique variational function, which is the master stability, which allows you to calculate the stability of the synchronization manifold for any possible network. And here, for example, you have the case of the Rössler system and the Lorentz system implanted into an hypergraph. Notice that here the coupling functions are inherently nonlinear, because we want them to be nonlinear. That is, we want them not to be factorizable into different pairwise interaction, and you obtain different classes of functions. For example, here you have a very nice behavior in which you have a manifold of synchronization which is unstable. Then when you increase the coupling, it becomes stable, then it becomes again unstable, then it becomes again stable. So you have different passages of stability of the synchronization solution depending on the coupling strength. How much I have? 5 minutes, you see? The last things I want to discuss to you is a probably very famous system, which is the Kuramoto model. In the Kuramoto model, everybody knows the Kuramoto model. You know, the only nonlinear thing is the interaction. Because if you don't have an interaction, Kuramoto model is derivative of the phase equal the frequency. So it's really linear. And now you can make two extensions of the Kuramoto model. The first extension is considering many-body interaction, that is putting the sinus of theta k minus theta I plus theta j minus theta I. But you know, sinus of A plus B is not A plus B. So you cannot factorize. So this is therefore going into many-body interaction. Of course, you have a double sum here. And the second extension was done in the group of Maryland by Edward Ott, which is you can take the Kuramoto model, which is a point in a plane, in the unit circle of the plane, and write the evolution of the corresponding vector sigma I of components cosinus theta I, sinus theta I, and write the equation of this vector. When you write the equation, you obtain d sigma I dt equal to an antisymmetric matrix because the derivative of cosinus theta I is minus cosinus. So you have an antisymmetric matrix. Plus this term, which is a function of the order parameter. This, believe Edward Ott, is just a question of a few trigonometric transformations. And now when you write this equation, you realize that there is no reason to limit yourself to 2 dimensions. The vector sigma can have any dimension. The only important thing is that it has to be norm 1. It has to be a versor, not a vector. And therefore, with the same equation, you can, for example, describe the alignment of a point in a phase, which is a classical Kuramoto, how the phase is locked, or in dimension 3, points which are moving on the surface of a sphere, and how they align their orientation, which is much more like a flocking, flocking of animals, of birds, which have to align the direction of the velocity. Or in dimension 4, how you are moving in the hypersurface of an hypersphere, etc., etc. So you can make this extension and this extension, and we did both in a recent Physical Review Letters, and now you have very interesting results. First, this is the normal Kuramoto, is the transition to synchronization, R is the usual order parameter, lambda is the coupling. So the first row, you see, first row is normal Kuramoto, 2-body interaction in dimension 2 and dimension 3. The second row is 3-body interaction, dimension 2 and dimension 3. Dimension 2, 2-body interaction is the classical Kuramoto. You have a second order transition to synchronization. So second order, continuous, reversible, everything. If you now introduce dimension 3, the second order becomes discontinuous here. See? And now if you put the 3-body interaction, you get discontinuities also at the level of 2-body interactions and double discontinuities at the level of 3-body interaction, with an additional important feature that going back, you reach for negative value of lambda a state with R different than 0. So a state which it corresponds to a partial synchronization or when the coupling is negative. And this is the news. So you have a new state which is inherently impossible because the condition, the necessary condition for the Kuramoto model to synchronize to have at least a portion of the population of the ensemble which is positively coupled to the mean field. And here you have an ensemble which is entirely negatively coupled to the mean field, which gives rise, thanks to the three-body interaction, to this. So this we demonstrated here that actually this is a limitation of two-body interaction, not a limitation of the model itself. Okay, so this has been published, I told you, in a recent PRL. This is the list of readings. If you want, I summed up many things, but I want you to understand that this is our main interest, these higher order interactions in networks, and they really give rise to new phenomenologies, new dynamics, not only to problems in network structure. And then thank you for your patience. Submit your papers to chaos autos and fractals. Here I put many people that are participate to this conference in many forums, which are editors of the journal. These are general numbers of the journal. We are the #1 now in the ranking of mathematical physics, #4 in statistical and nonlinear physics, #6 in general mathematics, #20 in applied mathematics. And these numbers are going to improve very much very soon. And as I already presented to DCC this morning, we have more than 1 million downloads per year and a very nice and selective acceptance rate. Thank you for your attention.
So, questions, comments?
Well, I have a question, but first of all, I would like to congratulate Stefano. I'm very impressed by what you found. It's extremely interesting work. And I have a question. What about if you move to the brain? Do you think that the dynamics of the brain might get some benefit from your approach?
Okay. So first of all, thank you for the question, because, for example, one of the evidences, recent evidence of higher order interaction has been right in the connectome of the brain. So there are people who found motifs that corresponds indeed to 3-body interaction and 4-body interaction in the brain. So evidently, there is a sort of architecture where this higher order interaction in the brain are essential. Still, we don't know why. For example, one interesting thing in Kuramoto, this is Kuramoto, it's not brain, so one has to go with other models, is that when you input the 3-body interaction, only 3-body interaction, this 3-body interaction tends to cancel the forward transition to synchronization. And they maintain the backward transition to synchronization. So it seems that this is very important for the brain, because, you know, synchronization in the brain is a pathological state, is a state of epilepsy. So it seems that these are sort of barrier which impede the, so to say, formation of synchronization to large scale. The brain needs to synchronize to small scale because they need to make in parallel different tasks. But they cannot go into large scale synchronization, because otherwise you would have a pathological state. And it seems that these 3-body interactions are distributed in a way that they really impede this. But, you know, this is a guess. There is a lot of study to be done.
Well, very interesting.
I would like to know if some of the more characteristic properties of simple networks, like scale-free property, small world property, if they have been identified also in real-world hyper networks. And I would also like to know if I correctly understood the hyper network study or simplicial complex study is a quite new area of study of a few years. If are there evidence can be useful to generalize the hypergraph models for multi-layer multi-layer interactions between, so multi-layer hypergraph networks.
Okay, so you made a lot of questions. Try to answer one by one. So the first question was whether you can find the scaling properties in hypergraph like the scale free and these things. The answer is yes. And actually you can have different scalings at different orders of interaction. So you can have, for example, an hypergraph containing two-body interaction and three-body interaction, where two bodies interaction are distributed with power law, and three-body interaction, for example, distributed like a Gaussian, or vice versa, or both power laws. And there are some generative models, not only done by us. We published this here, one generative models, but there are many other generative models, for example, by Ginestra Bianconi and the people in London, which describe the way and the processes through which you can mix these things. So the answer is yes. Second question, this is a relatively new study. I wouldn't say so. I mean, simplicial complexes are known to mathematicians since 1953. So it's a very old concept which was almost left in a box up to when indeed it was found that this many-body interaction have a role in real networks. So they immediately opened the box and found some part of the theory already made. So it's not so new in mathematics, but it's certainly new in networks theory. I consider this really the new, so to say, perspective of network theory, because these are objects, thanks to this higher order interaction, which produce different dynamics, as you saw. And therefore, it's a much richer scenario which needs to be addressed. And the third question was if this has something to do in connection with multi-layer, or you can, multi-layer network, if you want, if you take it alone, I am not such a tremendous fan of multi-layer network, because I still don't understand which is the basic difference, conceptual, between a multi-layer network and a normal modular networks. The moment you write a supra-Laplacian matrix, you write a network, which is made of moduli. And each layer is a moduli. So you have the interlayer, intralayer is what you have inside, outside the modulus. So it's a nice representation, the multi-layer, but I wouldn't think this as a new concept. This is a new concept because you really need a tensor. You cannot describe this as a matrix. It's a different mathematical object. If you can do into multi-layer hypergraph, yes, but nobody did that so far because there's still a lot of questions open at the level of monolayer, so to say, multi. But you can imagine to have, nodes in different layers with different hyperlinks that are connecting them, and a structure like a multiplex, for example. And this is also a very nice perspective. Maybe it's worth trying if you want to do it.